So today is lecture number 32 E524 Digital MOS LSI circuits, and today is November 6, 2020. We have started with the memories, and we learned that how the memory array is actually created, right? Like this one, where you have row decoder, column decoder, one of them is address and one of them is data, right? And also we learn the most important part, or you can say that we have given most of our time for designing CMOS inverter, and we'll become expert of it. And it's very important topic in terms of designing not only combinational logic with respect to the available ratio, but it's also important to design the sequential circuits, where the important block is the latch. So we have derived all other sequential circuits using this latch. If it is a static, if static sequential circuits are there, we have used this latch. If it is dynamic sequential circuits, then we have used switch and then cap. The switch might be with NMOS, PMOS, or it's with the transmission gate. So these things we have learned it, and we also learned that static is the one which is actually keep the data for a longer time, and it's not changing much. However, in the case of dynamic circuits, dynamic sequential circuits, the data is not remain for a longer time, it's for a smaller time. That's why it has to be refreshed time to time. And this is the popular technique through which we are designing dynamic circuits, and this is the technique through which we are designing a static sequential circuit. So same is going to be extended in a case of the first class of the memory, which is called SRAM, or the static RAM. RAM is random access memory. It's so it can read, it can write both, and we are on the first classification side here. So we are learning about static RAM. So what static RAM look like is actually coming from this particular block, which we are going to see maybe in the next slide. But before that, static RAMs use a memory cell. This memory cell is nothing but a cross-coupled back-to-back inverters with internal feedback that retains its value as long as power is applied. Notably, this all these static RAM are the one which can retain its value until power is there. If power is not there, the value will not be retained. And it has following attractive properties. So it has denser than flip-flops. It's compatible with standard CMOS process. So that's the best part, because lots of money has been pumped in the CMOS process development in various countries and even in Silicon Valley. So of course it has to be compatible with standard CMOS process. It's quite faster than DRAM, which is dynamic RAM, and easier to use than DRAM. However, this DRAM compared to DRAM, SRAM is quite old, and DRAM was invented later. The static RAM came. That's why like static RAM has all the business earlier, and thereafter people started using DRAM. However, static RAM is faster, and still it's easier to use because it has this positive feedback. Note that when this dynamic word is coming, and we are all the way, we are also doing this whenever there is a memory, it's also the sequential process, either it's static or dynamic. So in the case of static, we are going to use this particular block, which is made up of back-to-back cross-coupled inverters, and for the DRAM, we are going to use something called a capacitor, right? The way we have used it in the dynamic sequential circuits, where we have used the switch cap circuits, and then like we have designed rest of the part where there is no back-to-back inverters, right? So this is what we have done, and that's why like the way its usage is, static RAM is much simpler. Now let's look at that, how this is going to be look like. As I told you, this is a single SRAM cell. When I'm saying a single SRAM cell, means this block I'm talking about, and thereafter it's going to be replicated many places, right? So it's the same block which is going to be everywhere. Right. So in this case, you might have seen that we have two lines going vertically. Okay, it's not shown over here, but okay, actually there are two lines vertically. Both of them are complemented to each other. By the way, this is not for maybe only for SRAM, that's why that two lines have not been shown. However, this block is surrounded by bit line and bit bar line, or you can say BL and BL bar, and other side it's word line or WL. Word line is going to decide which address has to be read or write, and bit and bit bar line are going to tell you that at particular address what needs to be read or what needs to be written, right? So write and read part is happening from here, whereas the address of which particular cell has to be read or write, that has to be from this word line. So this particular block is known as a single cell. Right? So this is a bit line, and this is a bit line bar. Note that just to understand the SRAM cell, we are moving very slowly. We are not going directly to the bigger part. Our approach will be the bottom up approach, where you are going to learn the cell, and then you are going to learn the rest of the things, like how these bit line and bit line bar are going to be precharged, and how it's going to work with the different clocks. So first, if we are interested in the SRAM cells at the bottommost part, so this is word line, and this is bit line and bit line bar. Bit line and bit line bar should be always complemented to each other. However, there might be some propagation delay, through which you need to check the output accordingly, right? So this is how SRAM cell look like, where you can select the cell using word line. So if word line is high, then you can read or write this particular cell, right? Depending on what has been kept on bit line and bit line bar. Note that all the SRAM cells or any memory cell are going to be written or read in two different phases. One is called precharge and one is called evaluate. When precharge is there, these two lines are known as the precharge lines, where you can precharge them to VDD. In one of the phase, let's call that phase as phi1. When precharge phase is there, bit line and bit line bar are going to be VDD, and no matter what line is there, right? So These two has to be VDD. When it's evaluate, means either you are interested in reading the cell or maybe writing the cell. In that case, you can do both the options, whichever you want, right? Either you can read, either you can write. Okay. So this was the thing. So now how this reading, writing, all this happens, let's look at that one by one. So by looking at this SRAM at the from the aerial view, we can understand that we need to have the weak cross-coupled inverters. We need weak cross-coupled inverters. When we are saying weak, we understand that I'm talking about its W by L. If W by L is very low, as low as the minimum, it's a weak one, and others are strong if their W by L are as high as possible or the required resistance. Look, nothing is happening in I would say that trial and error. It's actually in terms of resistance and capacitance. Resistance and capacitances are depending on W by L. As you are increasing W by L, resistance is getting decreased. When you are increasing W by L, capacitance is also increased with the fact that it's W times L times Cox. And of course, it's also depending on the fact that which particular region you are working in, right? So accordingly, you can have the required resistance and capacitance. A multiplication of these two are going to decide the propagation delay, and multiplication of that propagation delay with the number 0.69 decide you are looking at 50%. If you are multiplying that with 2.2, it's multiplying with 90%. If you are looking at according like 10%, you have to change the value. Or if you are interested in checking the value exactly after it's getting the settled, you need to see what is the time constant tau completely without multiplying that with any number. So this is what already taught, and we also learned that there is no problem. Now the positive feedback here, which has two inverters back to back or four transistors in a cross coupled positive feedback manner, it is actually correcting the noise or the leakage. So if you understand correctly, any of the node requires, let's assume that one line is not connected and you have some value. So let's assume that this is 1 volt, this is 0 volt, and this is Q and this is Q bar. So the Q and Q bar might be complemented to each other. However, Q, if it is flipped by a small value like this, then Q bar will also be changed with some delay. That delay is from this inverter. But look at this. If Q is not changing the state from, you can say that from the given noise margin high or noise margin low, it will not flip the other side. You have to go beyond the required noise margin, or it has to be as a part of the noise margin. If you remember, the noise margin high and noise margin low, right? So in that it has to be changed. So this is what very important thing. Or you can say that because of this positive feedback, if the noise margin is within the limit, then it will flip the other side, right? Or you can say that small bump above the midpoint or below the midpoint, it can flip the value at the other side, right? So this is what this meant for the positive feedback, corrects the leakage or the noise. If there is any leakage, noise or anything, it will be corrected, right? Because of this positive feedback. This also studied in the case of the Smith trigger, right? Anyway, so let's, by the way, this particular cell having 6 transistors, that's why it's known as the 6T SRAM cell, which is referring to the 6 transistors, right? Now this 6T SRAM cell has two phases of operation. One is called phi 1 and one is called phi 2, right? One is pre-charge phase. So here phase 2 has been defined as pre-charge, and phase 1 is either read or write. Let's not going into this right now, but let's understand what is read and write at the first place. In that case, pre-charge will be understood maybe after that one. But before that, how to read and write, let's start with the read operation. I'm drawing this for you one more time. So this is bit line. Let me give the same name. Okay, bit line and bit line bar. Let's give the same name what is given in the book so that you can follow easily. So bit and bit bar. This is Q and Q bar, and these two transistors are governed by word line. What the name given here? Word. Okay, so I'm giving the same name. Okay, so here I'm interested in reading the cell. But as I told you, before reading, there is always a pre-charge. So at the beginning of reading or at the beginning of writing phase, these two lines must have pre-charged. As the name suggests, it's pre-charged to VDD. So both of them are at VDD. No matter what word line is at, but these two lines are at VDD. And in the phase 2, I'm going to make it floating. Right now it's VDD. This is also VDD, but the cell might have some value available over here, Q and QB, which needs to be read. When you make it floating, and when the word line is on, you can see bit and bit bar are going to be filled with the value which is actually there. If Q is equal to let's say 0, then this bit is equal to 0 and this bit bar remains at 1 after some time. But this is not so straightforward. You need to do it with some sort of designing. Although when we have started this, we have written that these cross-coupled transistors or the inverters has to be weak. But that's not true. Let's understand why. Let's call these transistors as P2 and D2, P1 and D1. It's a reverse of that. P1. Let's call this one as A1 and A2. So I'm calling A1 and A2 are access transistors. And D1 and D2 are the driver transistors. Okay. So let's assume that I want to read the value when, okay, it should be when Q equal to 0 and QB equal to 1. I want to read this, right? So, but At the end of the precharge, both are VDD. So now these two are not going to change, right? This is already 1, this is already 1. But this VDD needs to be changed to 0 because that is what I want to read at this side. So now what is going to happen if this is 1? If this is 1, then this is 1. I made any mistake? I made mistake in drawing this, right? Right. So this is D2, P2, P1 and D1, and this is Q and Q underscore B. As we know that QB was already written 1 and this one is 0. Note that when precharge was that this word line was not high, but when word is going low to high, this is word going from low to high, at that time Q was 0 and QB was 1, right? And at the same time bit was VDD and bit bar is also at VDD. For simplicity, I am not drawing it. Okay, so right now, when the word line is not going from 0 to 1, this is the situation. Now, when Q equal to 0 and I'm making this word also equal to 0, let's redraw this. Maybe I can do it here itself. If QB equal to 1, it's going to make following transistor in on mode. So this is on, right? And yeah, so if this is 1, what is going to happen? This particular node has to be connected to 0, and in that case this has to be on, right? And other place where it's not drawn, those two are off condition. But all these things happening in actually without understanding the fact that the Q node looks like this one. Where this was already written as 0, right? After having this word line to 1, bit line to 1, where bit has to be flipped, right? So in that case, what is happening? You can see this switch as either of the way because this transistor is symmetric, and like this value can also go this side and this Q value can also go this side, right? Right now this is also, you can say, floating or ready to get some value, and this is also ready to get value. So what value will be transferred at other side? We know the answer that I want to take this value to this side, not this value to this side. So how this is possible? This is only possible with the fact that we need to see that what is the minimum resistance path. As per the electrical engineering, we have to understand that the current flow will happen or will see the minimum resistance path. So where I want to see the path, I want to see the path that in these two path 1 and path 2, I want that this does not change, right, and remains at 0. And when this is on, this 0 can move other side. In that case, which resistance has to be more? This resistance R1 has to be much higher than the resistance offered here, R2, so that 0 remains here. If this becomes open or high enough, then this particular transistor, which is known as A1 and D1, right? A1 and D1. So what I propose in this case, if XS1 transistor is weaker and D1 driver transistor is stronger, then such thing will happen and 0 will remain here and strong, and A1 is weaker. This bit bar is going to, bit line is going to get at at 0 with the propagation delay associated with A1 and the capacitance at seen at bit line. So with that, this should happen. But note that before doing all these things, look, when you are doing all these things where everything is associated with the resistance, capacitance, and the switches which are going on and off, right? So this Q cannot remain exactly at 0. When this is at VDD and this is on for some times, for the getting it settled to 0, this will also go little bit higher, and then it will come down, with the fact that this D2 transistor is stronger than A1 transistor, which is weaker. So there'll be a small bump, and then it gets settled down to 0 because of this bit is also settled down to 0. And all these things happening with the fact that, look, there is a positive feedback. So if you know that if this is the switching threshold of the combination of P1 and D1, or the combination of P2 and D2, which are the transistors. So if this Q is going beyond this, then what will happen? This will considered as 1, and it will make this transistor off, these two transistors off, and others will become on. So it will flip the value. If this will happen, somehow if Q reaches the switching threshold, then it will flip the value. But if it is remain below that, means I kept it is such a way that it's strong enough and the noise margin is such a low one, this is not going to happen. Or what I can do, I can simply take this one little bit upside so that it does not go up. So in that case, the second condition which remains over here is, so this was the first condition to make it work. Second condition, which is associated with the fact that right. So this is with the fact that if this is 0, then it's making this transistor on, this transistor on, these two are off, and hence this QB remains at 1, or you can say that VDD, because that is what we are expecting, because we cannot read this one. If you are, even though you are going to read it, you are going to read only 1. But if you are reading from here, which is associated with the flipping of the bit, so here the most important part is A1 has to be weaker, D1 has to be stronger, and the Q has to be lesser than, or you can say that Q's value has to be lesser than the P2 and D2. Sorry. Yeah, P2 and D2 transistors switching threshold, right? Because if it is, even though you keep A1 weaker and D1 stronger, but if Q is not lesser than the switching threshold of P2 and D2, then it can have the possibility that it can flip the bit, right? Okay. Any problem, Sachit? Sorry, Nandit. Okay, so what is the doubt?
So if even resistance is high, then how Q is shifting to that side, 0?
It's a relative high. It's not saying that A1 is high that this becomes open circuit. There are two paths.
If D1 is strong, stronger, its resistance is lower as compared to A1.
So there is always a connection to 0. So this Q remains at 0, and there is a minimum impact coming from this side. If there is even impact is coming in terms of current. Look, there are two different branches. So there are two different branches. Right? So there are two currents, right? Either of the side, like it might be the direction wise, it might be negative, right? So my first thing is this Q should not change to other value because of VDD, right? My main objective is that, because this is the bit line coming, which was already pre-charged, and that's why this is happening, and this is at VDD. If this D1 transistor is weaker than A1, let's assume that, then what is going to happen? This VDD will try to reach here, right? Right? If D1 is weaker than A1, means smaller resistance is over here. So Q prefer to go to VDD. If A1 and D1 are exactly identical, let's assume the case when both are identical, then what is going to happen? Both the resistances are equal. In that case, Q goes to VDD by 2. You agree with me? If A1 and D1 are exactly same, both have same resistance. So one of the resistance has to be more to get this 0. When this is possible? It is possible when this resistance is as low as possible compared to R2. Still there are resistances. Look, you need to find out the ratio. So as I told you, like if you're keeping both of them as equal, what is there is most likely chance that you are reaching switching threshold of VDD by 2. I don't want that. I can do one thing. Let's keep Q lesser than VDD by 2, and let's keep this switching threshold higher than VDD by 2, so that it cannot reach there and it cannot flip the bit. Now any problem? Okay, because this concept is looks simple, but still it creates lots of problem. Okay, if no problem, then I can move further. Any problem from other side who are online?
Hello, sir.
Yes, yes.
Sir, it's Mushfiq, sir.
Yeah, Mushfiq, tell me.
So, sir, which one is the easier method, sir? Keeping the switching threshold higher, sir? VDD by 2.
Both. Both.
Okay, sir.
So this one has to be higher, because look, this is one side of the story. I'm saying that it's only the reading part. When
Yes, sir. Yes, sir.
writing has to be done, there has to be like something has to be done for access to transistors and maybe other transistor also. Then it's a trade-off. Then we can derive. Right now we don't know what is going to happen in writing, right? So in the reading part, let's make it that there are two options, and we are going to take that D1 stronger and A1 weaker, and Q lower than. So both we are going to take, not only one. And then we will move to the right part, and from write and read both, we will find out what will be the value of D1, D2, P1, P2. This looks a smaller thing, but still people are doing lots of research, and still people are publishing papers on 60 SRAM. Right?
Yes, sir.
Okay. So any other question from other side? Like, yeah, you can ask, no problem.
वो सर हमने Q इक्वल टू 0 रखने के लिए हमने A1 वीकर और D1 स्ट्रॉन्गर तक Q इक्वल टू 0 रहे वहाँ पे.
Yes, because this cell was already written with the values 0 and 1. So
फिर वो सर उसमें कैसे बिट लाइन में कैसे रीड हो रहा है उसी.
because of this VDD line. Look, okay, I understand your question. So let's understand that this is bit and bit bar, which are precharged to VDD, and there is a cell not connected to these two lines. At that time, it's written this side as 0 and this side as 1. You can do either of the side. If you do actually reverse of that, like this case, this is 1 and this is 0. Now, whenever you want to read, these two lines are available outside. If you look at the whole structure, look, you are not reading inverters individually. Look at this. You have availability of following things: bit lines, word lines, right? And through that you are reading the things. So bit and bit line are the only one through which it can be read or it can be written. So if I want to read this one as 1, when I'm saying that, let's read by making this cell 1. By the way, this is a word line. This is coming because of the address. That address from the top side, I know that I need to read this particular cell. So in that case, when it's being read, look, this is 1 and this is 0. So there is no fluctuations I'm expecting over here. But I need to make this 1 to 0. Right? This I'm expecting to change. Now, there are two things happening over here. Right. So as we have done it here, this is connected to right. It's like this. I'm not drawing the rest of the circuit, right? So this is, let's say, driver transistor, and this is access transistor. In this case, if I leave it as it is, what is going to happen? There are two switches are there whose gates are connected to VDD, means both are on. I can draw it this way also, right? Because it's all about illusion in mind. So if this is cubic, if it has to be 0, what is going to happen over here? If this is 1, this is 1, two things can happen. Look, this is already at 0, this is already at VDD. What can happen? It's a unidirectional. Look, like either 0 can be passed here or VDD can be passed here. To influence this line to change from VDD to 0, the resistance here has to be more, so that look, this 0 can transfer over here without changing this. If you remember, the resistances we talked on the basis of that is going to be changed, right? It's all about fighting in terms of resistances, and at the end, of course, the capacitances at the available bit and bit bar lines, right? So that is how it's being read, okay, in any of the side. So if you want to read it, so it's only possible to, like, the best example is the one when one line is going from VDD to 0. So one of the line will going from VDD to 0, and the one which is not changing, it's remain at the place where it was, right? So that is not a problem. Other side is not a problem because all side it's VDD. So there is not much changing, but changing is happening when these two transistors are there. So this is only possible. So if you want to transfer this 0 from here to here, we have to make sure that this 0 should not change. If this is changing, because this is going to change, of course, because when this is on, look, this VDD will also try to come this side. So in that case, this Q will go up because this is coming down, right? Okay. So if both the resistances are equal, then both will cross, right? And this Q will go up and this will also go up afterwards, right? So this is going to happen, right? So this was about the reading part, right? But if you look at now little bit one level up, where I told you that we are precharging the line also. So there are two phases, phi 1 and phi 2, and this is the SRAM cell where it's connected with bit and bit bar, which are actually connected to some bit line conditioning, or in a particular column you have so many SRAM cells like this, where these lines are getting recharged by the phi 2 bar. If phi 2 bar equal to 0, means in this case bit V1 F, which is this, it's going to be VDD, and of course bit bar, which is not drawn over here, but bit bar V1 F is also going to be VDD during the phase when phi 2 equal to 0. So that makes phi 2 bar equal to 0, right? So in that case, these two are precharged to VDD, no matter what word line you are connecting, right? So in that case, you can, whatever is available here, you can read it through some high skew inverters, right? And here you can see that there are two phases. One phase was precharge. So in that precharge, these are at VDD, and when phi 2 is on, sorry, phi 1 is on and phi 2 equal to 0, you are in the next phase where you can read or write. Let's assume that you are reading, but at the same time, this line has to be also equal to 1. Otherwise, you can't read it. Both the lines will remain at VDD only, and it's not going to change. But if this is at, you can say that green part, then as word line is going from 0 to 1, with the propagation delay associated with this SRAM cell, it will flip bit V1 from 1 to 0, as we have already learned, right? And if this is changing from 1 to 0, this particular part b1 v1 r is also going to change from 0 to 1, and you can see there is a finite propagation delay. This is because of this H transistor or H inverter delay, and this delay, it's because of SRAM cell delay for reading the cell.